Chemical Engineering, Polymer Science 757, Polymer Rheology, H.H. Winter, Lecture 14a. The relaxation spectrum of long linear molecules in the molten state, in all molecules being of the same length, is very simple. And that's convenient for us because we can just measure the relaxation behavior of that material and analyze the data. And from that analysis, we obtain a spectrum which follows just a power law. It's a simple spectrum. We can formulate that in a simple equation. It's a so-called self-similar behavior, saying that the whole chain relaxes in the same fashion as smaller and smaller parts of that chain. Somehow this it should be possible to formulate that from first principles in physics, but that's just a result we are getting from our experiment. We discussed that the whole class before that. Here I brought some data just for you to see again. This is the experimental data set G prime of a monodispersed polymeric material. If you please extend the frame. Oh yeah, it's okay. So this is polybutadiene standard measured by Mike De Rosa. G prime at 4 different molecular weights. This is the highest molecular weight, having a breakpoint at low frequency at long times, and then at shorter and shorter times as the molecular weight is smaller and smaller. The counterpart is the loss modulus, as shown here. Again, it's a very simple pattern we are looking at. We have a breakpoint in the spectrum. There's a linear region in the entanglement regime of the material. And then at short times, at high frequency, there is a transition to the glass. Now, this pattern has been analyzed, and the result was a simple self-similar behavior which consisted just of a straight line in a log-log plot. This is h of lambda, and it was cut off at the longest relaxation time. You can see that the highest point is constant, is independent of molecular weight, expressing the plateau modulus being independent of molecular weight. And the cutoff is proportional with the molecular weight to the 3.4 power. And that type of spectrum we wrote down just for this linear region. We said that h of lambda was given by a constant, which is just n times the plateau modulus times lambda over the cutoff, which is lambda max, to the n power. N in our case was about 0.2 or 0.25 in that order of magnitude. And this is valid for lambda smaller or equal lambda max if we neglect the glass transition behavior. Now, that is a very nice result, and it relates directly the molecular structure to the relaxation behavior. Today, I want to come back to this type of approach and see whether we find similarly simple relaxation spectra for more complicated structures. For the list here for Polymer Solutions, for instance, here we will look at the relation between the relaxation time spectrum and molecular parameters, and we will look at a dilute solution and then semi-dilute and concentrated solution. All of those taken for linear, flexible, monodispersed polymeric materials. And then later on we will look at star and at branched molecules. Then we extend our analysis to binary and quaternary mixtures of monodispersed polymeric materials. And then later on we would like to broaden the distribution, have a continuous distribution, and see what's the spectrum for all of this. Let's start with the polymer solution. Now, in the literature, you find very often that the knowledge of polymer solutions will tell you everything about polymer melts, or vice versa. And as you will see, it turns out that polymer solutions have a much more complicated relaxation spectrum than polymer melts. It's a binary system, and we will not be able to represent the relaxation of the solution in a simple fashion as you just saw before. Actually, it's a rare exception to have a spectrum like we found for the melt for the monodisperse polymer. So let's look at the polymer solution in the very diluted state. That's a system where the polymeric molecules are separately floating around in the solvent. They are separate entities. Like here, you could model them with little balls. In fact, Einstein was interested in the viscosity of a system like that when he derived the model for polymer suspension, for the viscosity of a polymer suspension. So in dilute polymer solutions, we treat the molecules as separate entities which are floating around, and in shear flow, those separate entities will increase the viscosity. The viscosity of the solution is equal to the viscosity of the solvent times 1 plus a coefficient here containing the concentration of polymeric material and the so-called intrinsic viscosity. Now, in Einstein's case, this would be 2.5 times the volume fraction of solid filler. If you want to extend this Einstein formula to larger molecules, to larger concentrations, then pretty soon a nonlinear term comes in and you can modify that. Now, the intrinsic viscosity depends on the molecular weight, because the molecular weight determines the size of those molecules, and the relation is given in the Mark-Horing relation. Now, note that this exponent is very small. It's 0.5 to 0.8 in that magnitude, so the intrinsic viscosity doesn't change too much with molecular weight. While for polymer solution, for polymer melts, the zero shear viscosity would go with a 3.4 power. It would be much more sensitive to molecular weight changes. So this is the intrinsic viscosity. It has the dimensions of here, 1 over the dimension of the concentration here, because this is a dimensionless term. So it doesn't have the dimension of poise. Now, for the nonlinear term here, the Huggins constant is in the order of 0.3 to 0.4. In good solvents or theta solvents, 0.5 to 0.8. And we have to talk about the solvents in a moment. That's a very important issue in polymer solution, because the quality of the solvent determines the size of the chain. So if you describe the chain by a random walk, where the molecular chain would be described here by a sequence of steps of length L and random direction. Every step has a new direction. We could add all those little vectors and could say the end-to-end vector from the beginning to the end. This end-to-end vector is given as the sum of all the individual steps, all those little vectors. And the magnitude now of this end-to-end vector is just r dotted into itself, or this expression dotted into itself here, this times that. And we can evaluate this expression for a statistically distributed system, freely joined chain, no restriction in this angle. In this case, the product of Li with Lj would most likely be 0, because they can adopt all probable directions. And then we end up having this r squared being equal to the number of steps times the size of the step square. So this end-to-end distance, or the square of that distance, is proportional to the molecular weight. Molecular weight, the total length of the chain would be n times small l. So with increasing molecular weight, we are increasing the end-to-end distance square. Now, if the angles are somehow restricted with a valence angle of theta, then you can derive a similar equation. Again, has n l squared and has this coefficient for the angle dependence. In in a real experiment now, you can measure the size of the spheres by light scattering, for instance. In this case, you would pick a so-called theta solvent. That's a solvent which is neutrally interacting with the polymer chain. So it's a solvent at the theta temperature. And then you could measure the radius of gyration, which is related to the end-to-end distance. I think this is the average end-to-end distance. Again, in L squared with a front factor. And this front factor, C, for most linear molecules is in the order of 4 to 10. And if you are stiffening the chain, if you're talking not about complete flexibility, this factor would be increasing. So in light scattering, this factor is a measure of the flexibility of your coils. We're talking about very flexible polymers where this type of value can be seen. Now, this is in a theta solvent. If you improve the solvent quality, you will swell the chain even further. So if the polymer chain favors the solvent, with the solvent neighborhood, then it will expand so that more solvent molecules can be placed between the coils. And then again, there's another factor coming in described by thermodynamics, which describes the radius of the chain compared to the radius in the unperturbed state, in the theta state. So that type of analysis is very well developed. It's techniques are known very nicely. They are known very well. They're used for characterizing molecules. Now let's go to higher concentrations. And this is where entanglements come in. That's where the relaxation time spectrum is going to be interesting. The very dilute solution is a Newtonian liquid, so the spectrum really wasn't worth discussing. But now if we increase the concentration, say beyond 2%, for instance, then the molecules start to overlap, and then we could talk about a semi-dilute solution, and then up to, if we have more than 10% polymeric material, then talking about a concentrated solution where the molecules are highly entangled, like in a polymer melt. So only 10% polymer gives you really very high entanglement states. And the question now is the spectrum of the concentrated solution comparable to the spectrum of the melt of the 100% polymer system? There are some very nice data in the literature by Colby. It's actually a study by Colby, Fetters, Funk, and Grassley of 1991, having appeared in Macromolecules. And he measured the spectrum G', G', for different concentrations. This is a polybutadiene. Maybe I should just show you the list first. It's a polybutadiene of very high molecular weight, close to 1 million. And it is dissolved in a good solvent, in PHO. The polymer concentrations go from 1. This is a highest this is pure polymer up here. And that's the system which we would describe with a BSW spectrum. So in this case up here, we could put our spectrum in. We would determine N. We would have the break term. This would be lambda max, right? And this would be the leveling off. This is the plateau modulus of the polymer. And then with those quantities, you can write down the BSW spectrum immediately. It fits the data very nicely. Somehow, the angle is steeper than with any other data I saw so far. It's steeper. It's an angle of 0.4 here. This slope in G'. This might be due to the high molecular weight, I don't know. Or maybe the material is especially monodisperse. Somehow it's hard to measure the polydispersity of a material at this molecular weight. The GPC is not capable of telling you whether you have a real monodispersed material or not. But Lou Feathers, the one who synthesized this molecule, is world famous for his capability of making real monodispersed samples. So maybe it's a nice monodispersed system, and maybe if it's monodispersed, you get a steeper angle. Or it also could be that it's just an instrument error. Has been measured in the System 4 many years ago, and the System 4 was known to have some problem with the compliance. It has been corrected in the meantime, but in old data, you really don't know. These are data of 85 or so. It's really come out of Ralph Colby's PhD thesis. Okay, so this is the BSW spectrum, has the typical features. And now look at the spectrum at less and less polymer concentration. Here you have about 50% polymer in this case, and you see more curvature coming in. This is about 30% here. And it loses its character, its specific character. Now here it's vanishing. Let's look at the equivalent curves in a different solvent. The same polymer now in a DOP, which is a theta solvent at about 15 degrees C. Now Colby did his experiments at 25 degrees, so it's a little bit off the theta conditions, but close enough. So the same polybutadiene now put in solution. The coils are not swelling as much because the solvent is not as good as before. And you again can see the BSW type structure up here. And then at 50% you have this, and going down to what was 30, 16%, and here you have around 8%. So we're going into the semi-dilute solution already. And you can see that the slope gradually disappears, and then it will change into something like this. Those spectrum, I calculated spectra for that, don't seem to have a characteristic pattern. At least I haven't seen it. Maybe when you look at those spectra, you will find something significant in them. So for the pure polymer, we have a simple spectrum, but for the polymer solutions, everything seems to be much more complicated. So there's an indication that the physics of a polymer solution is more involved than the physics of a pure polymer system. One other source of possible error in these experiments I forgot to mention. If you measure a polymer solution in a cone and plate rheometer, then your sample has a free surface. Across that free surface, you might lose some of the solvent, and in effect, your polymer concentration might not be uniform throughout the sample. You might have a more concentrated polymer solution near the outer edge of your cone and plate rheometer than in the inner part. Now, the outer edge of your cone and plate rheometer contributes to most of the torque. I think about 10% of the outer edge of your sample contributes more than 50 or 60% to the torque signal. So if you have small amounts evaporating, you will have drastic changes in your data. And this is the simple reason why so few data are available on polymer solutions. It's very difficult to get good data. Now here, the researchers took a solvent which has a very low, very high boiling point, or it doesn't evaporate very easily, very low vapor pressure material to overcome that system. Now, another polymer solution I took from the literature is a system out of MIT. If you just look at the specs here, it's a polyisobutylene. It's not narrowly distributed, just a high molecular weight material, commercial polymer, and it's dissolved in polybutane, and to increase the solution speed. We're talking about weeks or months of preparing a solution like that. To increase that, it was some tetradecane was added. The mixture of those two gives a Newtonian solvent, and they had 95% of this 1,000 molecular mass polybutene and about 5% of the C14 chains. Now, into that Newtonian solvent, they're adding polymer. And in this case, we have 31% polymer. And look at the relaxation time spectrum. 31% by weight polymer. It's a concentrated polymer solution. Now, those guys are plotting eta prime and eta double prime. You know that this is going with eta prime goes with the storage modulus, and eta double prime goes with the eta prime goes with the loss modulus, and eta double prime goes with the storage modulus. The interesting feature here is shown here in the dashed line. They try to model the data with a single Maxwell mode, just one relaxation time and one fun factor. And that's been done in the literature extensively. Those fluids often are called Boger fluids because Boger suggested a polymer solution like this, a solution which is very viscous, so the high viscosity of that Newtonian solvent is very dominant, but the presence of some macromolecules introduces elasticity in that system. And people were looking for material which has a constant viscosity, no shear thinning, and and elastic behavior. But it turns out that even in this case, one needs a spectrum of relaxation times. This spectrum has been calculated here, has been given in the literature. Actually, here it's in Journal of Rheology where all of this appeared in 1990. And they found that an excellent fit, this is the same picture again, an excellent fit is achieved with the 4 relaxation times. Very similar to what we are doing. Experiments have been performed at a series of different temperatures, and then time-temperature superposition has been used to shift those curves. These polymer solutions are very temperature sensitive. You have to control your temperature very, very nicely. There was 1 Kelvin in temperature difference would give you 8% in viscosity difference in that system. 8% in your viscosity. So it's another difficulty in working with those solutions, the high temperature sensitivity, and you will appreciate that when you do your first experiments on a rheometer. So in summary about those solutions, the spectra, relaxation spectra, are much more complicated than the spectra of the polymer melt. We looked at polymer solutions taken from monodispersed polymer, and and those spectra have not been simple. And then at the end, you saw the spectra of a broadly distributed polymer, and that, of course, is very complicated. We wouldn't expect any easy analysis. So for that, we just would take a set of relaxation times and describe that. Okay, so much about the polymer solutions. Now I want to ask you a question, and that's this. The question is, can we extend our knowledge? I wrote it down somewhere. The question is the following. Can we extend our knowledge of the spectrum for the monodispersed polymer to understand binary polymer blends? In binary polymer blends in the sense that we have 2 monodispersed polymeric systems mixed. All of this above the above Tg, here we would produce binary blends far away from the glass transition temperature. We would look at flexible molecules, linear molecules, and then in this case we would have short molecules. This would be the S component, short molecules, but above entanglement molecular weight. Well, it should be still sufficiently high. And this should be monodispersed. And then we have a second component, the large molecules, where the molecules are longer, and again should be monodispersed. And you can take the ratio of those two so that the longest relaxation time is fairly far apart. The longest relaxation time goes with the molecular weight to the 3.4 power, and you can then just choose the right pair to get an interesting blend. Now, you have seen data of that type. I use them to discuss the relaxation time spectrum, the determination of a relaxation time spectrum. Just that time I took data of Schausberger, and this is the spectrum we were using. In this case, just G prime, G double prime, where the storage modulus in the terminal zone has a slope of 2 and G double prime slope of 1. And then the entangled region is somewhat bumpy. It has 2 regions, and the plateau modulus, the overall plateau modulus here is about the same as for the monodispersed system, and G double prime is following this type. And at that time, we just wanted to model this data set, and we were fitting it with the parsimonious model with just a discrete set of relaxation modes. In this case, we took 9 relaxation modes. Here, just to show this very quickly, we took 9 relaxation modes to fit G prime, and the same. You can see how nice the fit is working out, and the same 9 modes are fitting G double prime. So this is the spectrum, the discrete spectrum, and these are the setting here. These are the different modes we were using. And this is the calculated G of t. This is the result of the fitting. And that worked quite nicely. But now comes the question, can we use the self-similar relaxation behavior which we found for monodispersed polymers to model the bimodal system? See, the modeling I showed just now was just arbitrary. We just took a set of relaxation modes and tried to achieve the best fit. But now we would like to use the monodispersed spectra. And actually, I would like to describe the relaxation behavior of the binary blend as a superposition of the 2 relaxation spectra for the 2 components. Such an approach has been suggested in the literature, for instance, by Doyle and Edwards, and also by other people. They basically, here in the Doyle-Edwards case, they said that the relaxation modulus is just the sum of the modulus you obtain for the long chains and for the short chains. There's a weight factor in front. That's the volume fraction of long chains and short chains. The overall plateau modulus is not changed in this case, so it's a constant. It's a material constant, which is outside. The broadly distributed polymer has the same plateau modulus as the narrow distributed polymer. There's an exception. If you have chains which are below the entanglement molecular weights, you can lower you can change the whole glass transition temperature. You can plasticize your polymeric material. So we're talking about chains which are all above entanglement molecular weight, and then this type of relation might be helpful. Now, the function, the relaxation function for the long chain and the short chain has been derived from first principles by Doyle and Edwards, and this is the function where we would put in the characteristic time for the long and the short chain up here. Okay? So that's an approach in the literature. The problem with this approach is that the Doyle-Edwards spectrum is not quantitative for the monodispersed material. So if you superimpose 2 of those spectra, you cannot expect that you are able to fit data. But we know the spectrum of the monodispersed now using the BSW spectrum, and then we can possibly shift those 2 on top of each other. We could say we are using 2 BSW modes and then describe the bimodal. And later on, we will use many of those modes and describe the broadly distributed polymeric material. So that's the general approach which was taken then by Michael Baumgartler in his PhD thesis to extend his result before. Okay, so let's stay with the bimodal systems in the moment. We would take data from the literature, bimodal blend. You just saw those data, Schausberger's data taking a molecular weight of 125,000 for the short chains and 750,000 for the long chains. And then we would say that the spectrum of that binary blend is just a linear superposition of the two individual blends. It would be the spectrum for the short chains plus the spectrum for the long chains, but somehow they are shifted downwards and sideways. Let me show you what I mean with that. Before I will continue with that in a moment. What I mean is the following. We would take the data which you saw before. This is the bimodal distribution here, 50-50 blend, and data points are shown here, and line is drawn through here. We'll explain where the line comes from. Let's take first the BSW spectrum for the short chains. This is G prime, this is G double prime. And the BSW spectrum for the long chains. This is G prime and this is G double prime. At the glassy region, they are about the same. Now, this region will be shifted down here to model this part, and so it has to be shifted down and over, and this spectrum here has also been shifted down and has to be shifted in this direction over. And then by just leaving the shape as they are, but by shifting them and adding the two curves, we get the fit we are having here. So let me repeat this again. We have a set of data. We have two spectra, this spectrum and that spectrum, and each of them is completely known. For this spectrum, we know the terminal time, we need the plateau modulus, and we need the slope minus n. Now, for the long chains, the spectrum is also completely given. But we don't know how much we have to shift each of those. Now we can just use a regression of the data and shift them so that the deviation between data points and those in the new curve is a minimum. And this is resulting in the curve which we are drawing here. Okay? Now, what happens to our spectrum? Here is a comparison of the spectra. The original spectrum of low molecular weight is shown here, and the spectrum of for the high molecular weight is shown there. Now, this spectrum has been shifted to lower values and to shorter times. This is the spectrum for the long molecules. In the vicinity of shorter molecules, they can relax faster, and they're kind of lubricated. And the short chains are hindered in their relaxation by the presence of the long chain, so their longest time is shifted to is increased, shifted to a higher value, and all of this also has to be shifted down because the sum of those two contributions will end up as the plateau modulus. So both have to be shifted down, and these shifts. The shift in vertical direction would be the AIs, and the shifts in up and down. Well, this is in horizontal. This is in vertical direction. This would be the B shift. And now let me come back to the equation we are using in this case. See, this was the total spectrum. We just said we take the spectrum of PS3, which has a cutoff time lambda 3, and shift it sideways and down, and then cut it off with a Heaviside function. And then we add the contribution of the high molecular weight. This is the PS5, so which has a cutoff time lambda 5, and again it's cut off here with the Heaviside function at a different times at lambda 5. And the shifting will be described by those four coefficients. Those are the only unknown in the whole procedure. Everything else is known from previous experiments. And so that's a very simple shifting procedure. Several researchers have worked on that problem. The assumption is that we can shift our spectra but don't change their shape. It's just a linear superposition of those spectra. And the question is, first, is that possible? Does it make sense? So we have to confirm that with data. And secondly, what are the shift factors? How big are the shift factors? And there were several proposals in the literature for those shift factors. I won't go in the details. At the end of the handout, you have lots of literature references with possible papers if you really want to study that. So Schieber, for instance, suggested the horizontal shift factors given by the molecular weight of the component and the molecular weight of the blend. And this would be the weight average molecular weight of the blend. Mi is just the molecular weight of the component, since we are talking about monodispersed components. And this exponent has been found to be in the order of 1.4. Now, the vertical shift, Bi, is given by the weight fraction of an individual component. If you have a lot of polymer 5 or whatever, if this is dominated by one polymer, then of course this should appear in this shifting factor. This should be close to 1 then. And this is a weight factor for the individual component, and there are some proposals how to calculate this. And Schausberger, for instance, determined this with a weight fraction in some empirical correlation. Now, the constraint in all of this is that the sum of the BIs for all components, if you have 5 components, the sum of all 5 is equal to 1, so that you get the, when you're summing up your component, that you get the plateau modulus of the whole system. Okay, so for the bimodal system, it's quite successful, what we are having. It works quite nicely. Now let me go to another system, another bimodal system of the literature, that by Watanabe, Hiroshi Watanabe in 1984 described a binary blend. Each of them is very narrowly distributed. It's about MW over MN of 1.05. And Michael modeled each of those components with a distribution of about, with a log normal distribution. So, and then he took different ratios of those components and calculated now in a mixing rule, with the mixing rule, the moduli, G prime, for instance, and G double prime. Now, note that this is the pure high molecular weight component, and this is the pure low molecular weight components. And we had values here on the sheet. What was the molecular weights? Well, I will come back to this in a moment. Okay, so if you take the low molecular weight component and only add 3% of the high molecular weight, you can see there's a drastic change in the terminal zone for G prime. G prime is very sensitive to adding a high molecular weight tail. And then if you put more and more high molecular weight polymers, it goes along those curves. Note that the mixing rule doesn't work so well at low concentrations of this long chains in the system. There are deviations between the model and the data. Maybe the linear superposition is not successful in this range. It seems to be most successful if you have a 50-50 blend, or if it's dominated by the high molecular weight contribution. Then the blending will goes very nicely. The G double prime, accordingly, here is not showing so much of an effect when you add some high molecular weight contribution. This is the loss modulus of the same blend, but then you can see the taking over of the high molecular weight compound, and again you see the BSW type shape coming in for the pure component 1. So that's a nice agreement. The mixing is very, very sensitive, or the blend behavior is very sensitive when you look at the recoverable compliance. So Porter, for instance, here, and Prest did lots of work on the equilibrium compliance of polymeric systems. So Michael calculated those for the two materials. Here we had 36,000 for the low molecular weight component and 521,000 for the high molecular weight component. So a different composition. Here you go to higher and higher weight fractions of the large molecules. The compliance goes to a maximum and then levels off. So this initial change in the compliance is reflecting the hump which you saw before in G prime. The hump, this if you add low, a small amount of high molecular weight tail, then you're getting this type of changes. Okay. Let me quickly show one more example. We got some samples from the BASF, and again, you see a binary blend, 40-60 ratio about, and two BSW spectra are able to model the blend very nicely. This is polystyrene, again, samples given to us from the BASF, and here would be the spectrum. We have the spectrum for the long chains and the spectrum for the short chains shifted, and you have a transition. The kink, of course, is somewhat artificial, but it doesn't matter because this doesn't, from here on, the higher values are carrying. So for the binary blends, the linear superposition seems to work in most cases, except for the extremes when you just add a little bit of polymer to a polymer one. In that case, if you have a low molecular weight polymer and add just a little bit of high molecular weight, that seems to be critical. But when you're in the 50-50 range, it seems to work very well, and the shifting seems to be described by simple shift factors like described by Schausberger and others. So let's take a break here and then look at more complicated systems. Go to Chemical Engineering, Polymer Science 757, Polymer Rheology, H.H. Winter, Lecture 14B. So now let's move the whole thing into the range of speculations. We started with firm ground in the monodisperse. It became a little more inventive, I would say, with the binary blends. And now, how about four monodisperse components mixed together in a blend, all of the same species. In this case, they are polystyrene. When I show the data, and we will model those by, again, linear superposition. We take the spectrum being a linear superposition of the four components, and each component has a shift factor, AI, BI, and we will use the same type of rules as before. The cutoff time is given by the molecular weight of each component. So this cutoff, the longest relaxation time, is not a free parameter. So the only free parameters are really the AIs and the BIs. This H is a Heaviside function. So beyond lambda max, this function is equal to 0. So you formulate the Heaviside function that you get this. It's maybe a negative Heaviside function. The data from the literature, or the data we got from Schausberger, as shown here. This is now the blend with 4 components, the same polystyrenes which you saw before individually. I only have to show the spectrum of the longest chains here of this component. This is the 750,000 chain, and all the others have the same spectrum, as you know. Now, by superposition of 4 of those spectra, we are modeling this curve, and you can see that the description of the data is very nice, very, very complete. Now, the resulting spectra from this fitting are the following. Here we have the spectrum of the longest chain, which has a highest point here and a cutoff there. Now, this cutoff is moved to shorter times, and this is moved down. We have a quarter weight percent, or 25 weight percent for each of those components. So it's really shifted down significantly. That's the contribution of the next lower, contribution next lower. And this is the contribution of the smallest molecule. This is the spectrum of the smallest molecule, and that is shifted to longer times and shifted down. So that type of a spectrum is able to describe the data very nicely. So why not taking an infinite number of those components and describing the distribution, describing the broad distribution, or describe the relaxation of a broadly distributed polymer. We will do that. We will take a broadly distributed polymer and just say that the molar mass of that system is given by the sum of individual components, and each component has a weight fraction W and a molecular weight Mi. And we have n of those components. Okay? And Michael did that in his thesis recently. He took a polymeric material. This is, of course, all of this is on the computer now. He took a material of 750,000 molar mass. And that he kept constant. He always takes this molar mass, and then he takes polystyrene information to break down. So he thinks he has a polystyrene of 750,000 molar mass. And he says the distribution of molecular sizes is following a log normal distribution. Now, if Mw over Mn is equal to 1, the perfect monodisperse, he has just 1 point. He has just one sample, and he can describe that sample with a spectrum. Now, if he has Mw over Mn 1.05, it's still very narrow distributed, but he has a distribution of, here, this is the distribution of weight fractions. Wait a minute, the red ones here. The red ones give the distribution. It's a very narrow distribution. Now, each of those distributions is following a log normal. And you should have that formula. This is the log normal distribution, where you have a maximum molecular weight somewhere, and the standard deviation is just given as the log of Mw over Mn. Please change that in your handout. It's just Mw over Mn. So that type of distribution Micha is using, and then as Mw over Mn is increasing, the deviation is getting larger and larger, and the distribution is broadening up. Okay, so those are the discrete components. He would like to calculate the relaxation spectrum. He picked 10 discrete components per decade. It's kind of arbitrary how you would like to digitize your continuous distribution. So he took 10 per decade, and then he took a spectrum. Again, he's now said that a linear superposition gives the spectrum of the blend. He has the different components here written down as we had before. And also for completeness, he says all of this here is only giving us the flow regime and the entanglement regime. Doesn't tell us anything about the glass. So at the end, you would add a contribution for the glass. And then you have the broadly distributed polystyrene, which undergoes glass transition. So what did he calculate? He used the rules for calculating shifting factors, which I had before, and he calculated the horizontal shift factors, AI, for the different molecular weights. Here he has these different components in his hypothetical blend. And he calculated the BIs, and again, for every molar mass, he gets a value of BI, and those BIs are distributed the broader your distribution is, right? For the monodisperse up here, you just have 1 point. Actually, you don't shift at all. AI is equal to 1, and BI should be equal to 1 in this case. That's also a check of whether everything is fitting together. So those are the only parameters he uses. Everything else is given. Given, for instance, is the spectrum of the monodisperse. Here is the BSW spectrum. We don't talk about the glass transition yet. So we're talking about the self-similar spectrum of the perfect monodisperse. MW over Mn is equal to 1. It's cut off here. If you have some broadening here, the spectrum is not changed down here, but you see that the transition is more gradual. Here it's going in, it's smeared out, and that's probably what we are finding in experimental data also. That's another reason for finding not a sharp transition, but some other more gradual thing. And then if you go to a molecular weight distribution of 5, you see a very broadly distributed spectrum. Now, 5 is not extremely large for many polymer applications. You could have blow molding grades or film blowing grades with MW over Mn of equal to 30. Okay, so in rheology or in chemistry, we try to look at the ideal polymeric system, at least at the university, and you can see that in practice, one looks for broad distributions. They have interesting properties. Now, in this modeling, we hope that at least the initial broadening can be described by this approach, by taking these data, by taking this model, and we now can calculate G prime, the storage modulus of the material, and you can see that the initial sample has a very sharp transition at the longest relaxation time, and this sharp transition vanishes. It's a broader and broader distribution, and in the same fashion, G double prime is getting broader and broader for those materials. Here and this slope here, we are gradually losing, so there will be a broad transition from the terminal zone to the glass transition, and the entanglement region is not as pronounced anymore. So that's what we would expect. Those are the general features in polymeric materials which are broadly distributed. So when you have a commercial sample, the transition most likely is quite gradual, and this is the reason why it is gradual like that. Now the crossover between G prime, G double prime is sometimes taking as a special point, G prime coming up very steep and overshooting, and then G double prime coming from the side, and there's one point where G prime is equal to G double prime. And that's shown in 10 delta, this point. 10 delta is equal to 1. 10 delta is equal to G double prime over G prime, and that's equal to 1. Now let's see where this stands when looking at 10 delta. 10 delta equal to 1 would give us a line like this, and you can see that the broadening of the distribution just moves the crossover between G prime, G double prime to higher frequencies. But there's no real significance there to that. It's used in polypropylene processing and tailoring polypropylene materials. Somehow the crossover, when it shifts sideways, changes with the broadening, and then moves up and down, it changes with the molecular weight or something like that. So they are very distinct relations. And people try to find those relations and use rheology, in this case, to improve processing, which is really a good thing to do. Now, how about the plateau module, the relaxation modulus, which Michael calculated from this broadening? You can see the narrow system has a very sharp transition in the plateau modulus. It has a rubber elasticity region here, which we extrapolated to get the plateau modulus, and then it decays very sharply. A broadly distributed system has a more gradual relaxation spectrum. And again, that's the typical fingerprint you should remember for broadly distributed materials. The viscosity is also an interesting parameter. The viscosity is somehow related to the molecular weight. Okay? Now, the molecular weight we kept constant. And when you see plots, say, of eta 0, there are famous plots always giving us eta 0 in a log-log scale over molecular weight, and it's a slope of 1 here and a slope of 3.4, and this is MW. Now, if we keep this MW constant, then eta 0 should also be constant, right? Should not make any difference. Well, we wanted to explore that and see whether it's really constant, and you can see that the viscosity depends on molecular weight. This is now in a log scale, so that the lower region is really stretched a little further. But you can see that the viscosity of the monodisperse is somewhat higher than the viscosity of a broadly distributed system, even if the molecular weight is the same. So it decays somewhat. But then beyond a certain MW over Mn, here, if this is 1, then we have the ideal polymer. If this is 2 or 3, then the viscosity is not affected anymore by the broadening of the molecular weight distribution. The zero shear compliance is another sensitive measure of the broadening. If you now plot again MW over Mn and compare the zero shear compliance with its ideal value of the monodisperse, then you see a power law behavior. It increases in a power law. It's a very strong dependence of this compliance on the broadening of the distribution. So if you look at polymer systems of different broadening of different widths of the polymer of the molecular weight distribution, then the zero shear compliance is a good quantity to look at, and that's very well known. To describe now our overall approach, the dynamic data, G prime, G double prime, should be converted in a molecular weight distribution. That's really what we would like to do. Before that, I changed the molecular, or Michael changed the molecular weight distribution and looked at the effect on G prime, G double prime. But now we want to reverse that and make rheology useful as a tool for determining molecular weight distributions, say, of polymers which cannot be put in solution. There are polymers which you couldn't run through your GPC. Take a Teflon, for instance, where you have a hard time finding a solvent, and if you have one, you should operate above 300 degrees C. Now, even your best friend will not give his GPC to you if you want to use it at 300 degrees C. But you can measure G prime, G double prime at high temperatures very easily. So we start with the dynamic data, and then we subtract the glassy contribution, because we only use the entanglement region and the flow regime to determine the molecular weight distribution. And from that, we would determine a discrete set of Maxwell modes. This would be the parsimonious model. And from those Maxwell modes, we can determine the spectrum itself. And that's, if those modes are not spaced too far apart, then this is a fairly easy step to do. Now, this H spectrum can now be described by a set of BSW modes, and from the set of BSW modes, we get a set of monodispersed fractions and their weight fraction. We get their molecular weights and their weight fraction. And then we have a discrete molecular weight distribution and can maybe convert this in a continuous distribution, something like that. So there is hope that we can pursue that objective. And we only can do that because we now know the relaxation spectrum of the monodispersed polymer. See, if we would not know the monodispersed relaxation, then all of this would be hopeless. So, but since we know the monodispersed, we can do that. If you know the results, it works very well. I'm not sure whether it works when you really, if somebody gives you a polymer, it knows GPC, and then you do the calculation, and whether everything is agreeable. But for polycarbonate, for instance, we got this from GE, typical commercial polycarbonate. Michael subtracted the glass transition glass behavior, so he has this curve, here the blue curve, and then he takes that spectrum and analyzes it in terms of a molecular weight distribution, and this is the sum of the weight fraction as a function of molecular weight, and you can see how you go from 0 to the complete polymer, and you get the distribution of molecular weights in that fashion. And that looks reasonable, but I think we should analyze this in greater detail. But I hope you got the general idea of the approach, and maybe you have some ideas how to improve methods like that. Okay, so in summary about approach, it's a phenomenological approach. We don't even talk about molecular motions. There are models based on molecular motion, and they are very interesting, and maybe we can combine what we know. The linear superposition seems to work in many cases. So, and if that linear superposition works, we just take the BSW spectra of the individual components. And the quantitative agreement is pretty good, surprisingly good. The limitations are, the biggest limitation is that all the molecules should be of high molecular weight, sufficiently high molecular weight. We should not have molecules below the entanglement molecular weight, otherwise our broadly distributed system would be plasticized and the whole spectrum would be changed. Just remember the data in Polymer Solutions, taking a monodispersed polymer in solution and how the addition of small molecules changes that spectrum so drastically. Now imagine you have your complicated spectrum, like here for the polymer blend, and then have a solvent effect in this case. Would be very, very hard to analyze. That's as much as I wanted to discuss about linear chains and their distributions. But I have another subject where I have a few more graphs which I want to show you. Some very interesting things. See if we know the spectrum of the linear chain and recognize that the relaxation is somewhat self-similar. It's a specific type of spectrum. Then maybe that information helps us understanding star molecules and branched molecules. Now here, this would be a star molecule where the chemist produces a multifunctional center point and attaches to the center point chains of uniform length. So all the arms have the same molecular weight. The parameters of this molecule is the functionality of the center point, and it is the molecular mass of each arm. The total molecular mass of that system is just F, the number of the arms, times the mass of each individual arm. So that would be the molecular weight. The arms are supposed to be flexible, monodisperse, and we are far above the glass transition temperature. So it's really the counterpart to our linear molecule, which we looked at before. There are data appearing in the literature. Got a preprint. This is a publication by Fetters, Kiss, Pearson, Quack, and Vitus. So a lot of collaborators, because you need somebody who makes the molecules and somebody to measure the spectra and to do some theory on those experiments. Actually, I think it's also just fun, to work in a big group. That's very often the reason some friends are getting together. So these spectra are measured for 4-arm stars at a range of temperatures, but the reference temperature is 25 degrees. So it's shifted into those. It's not clear what the molecular weight of those stars was, because in the table there are 8 species, and I only have 5 of the data curves, so I don't know what Fetters meant here in those. But interesting enough is the shape of the curves. There's somehow a power law region coming in. Look at this. It's a straight line here, but it is not really a power law. If you take the spectrum, this would be now G prime, and I have G double prime, I believe, here. And if I put those on top of each other, if you just take the star with the longest arm here, this one, you see you have a straight line here, and I'm rotating this, I shouldn't. This is a straight line there, and then goes in the terminal zone, slope of 2, slope of 1, that's okay. But it's a very complicated shape. And then at high frequencies, it ends up in a plateau modulus, and maybe it ends up here in a slope, as we saw for the monodispersed polymers at higher change. And then there's a transition to the glass here at higher frequencies. So it's a very complicated behavior. I made a copy here. Here you have a comparison, even in the same papers. In the same paper, Fetters and co-workers show. This is the monodisperse. This is very nicely described by the BSW. This slope is about a quarter. If when I take here my pencil, and it's about 3 down and 4 over, something and 12 over, or 11. And see, that's nice. When you know the spectrum, you just do a few things, and then you already have your parameters of that spectrum. And a year ago, we didn't have this available, or 2 years ago, we were just comparing shapes, and now we're quantitative about the spectra. And here you can see the change due to the long arms coming into the spectrum. It's a great puzzle. If one of you looks for a nice project here in this course, you could take this data and just calculate spectra and see how they are looking, and explain all those spectra to us, and look at the paper associated. Would be a very nice spectrum. Now, instead of arms on a single joint, so instead of a star molecule, you could look at branched molecules. Branching occurs in cross-linking polymers, and with increasing extent of cross-linking, you get bigger and bigger clusters, and you have segments here connected by multifunctional cross-linking points. So this type of molecular structure occurs in many real polymers, and the question is, what's the relaxation spectrum of that? Now, Rubinstein, Zurek, McLeish, and Ball wrote down a theory saying that one could use a tube model. You could assume that this type of star is in a tube-like constraint, and if the end here, let's say if you want to relax this part of the molecule, then this arm has to come out of its tube-like constraint, and this come out of its tube-like constraint and go into new conformation. But then if this is done, then that segment also has to come out of its constraint together with those two. And this author now claim you should use a hierarchy of relaxation phenomena. This would relax first, this would relax next, and then this would relax next. And this only can relax if those two are relaxed and those two relaxed, need this other relaxing. So they have a special type of hierarchical fluctuations model which describes the behavior in an interesting fashion. And they indeed calculate a relaxation modulus. See, they don't calculate a spectrum, they calculate the relaxation modulus, and they find a power law behavior. Here you could describe this spectrum here with a power law region, and then this is cut off when you hit the end of the molecule. The finite size of the molecule gives you a longest relaxation time. And then there's a distribution of short amounts. So in their model, they're saying that the stress is due to the anisotropy of the chain segments, whether they are at the end or in the middle. And the stress only can relax by motion of the arms. So the arms have to relax, and everything occurs in a hierarchical fashion. And they say that the end of the chains, even when they are relaxed, that they are acting as a solvent for the chain. You know, when they're moving out of their constraint, they are not only released themselves, but they are releasing their surrounding. I guess that's what they're saying. So from a molecular dynamics model, these authors are able to describe the relaxation of a complicated molecular structure. Now, when they wrote this model, they didn't know about the relaxation of the monodispersed polymer. So they could combine now this information with the relaxation of stars. So I'm quite optimistic that eventually we will be able to understand the relaxation of more complicated systems. That the understanding of the relaxation of the monodispersed material is just the first step in a broader scheme. And for you, it's comforting that there's a lot to be done. We only know the most basic element in that problem. All the more complicated architecture have to be understood, and new generations of rheologists have plenty to do. That's all today. Next time I will talk about gelation.